On the table here I have plastic material samples that have all been molded using the same tool. They look the same, but these have been made from amorphous thermoplastics and these from semi-crystalline thermoplastics. What is the difference between them? Here it comes from a plastic product designer perspective. In order to understand the difference between amorphous and crystalline, we have to take a look at the polymer structure of these plastics. That would require some sort of a super microscope, which I don't have, so I will draw you a picture. The polymer structure of amorphous plastics looks pretty much like this. The polymer chains are just randomly oriented all over the place. They don't have any real orientation or direction. How is it with semi-crystalline plastics then? They actually look pretty much the same at the time when we have just injected them into the mold, when they are still like in hot and melt state. But when the material starts to cool down and it crosses so-called crystallization temperature, which is a material specific value, some of the polymer chains, not all of them, start to arrange themselves or coil up into these dense packages that we know as crystals. So in the end result, in room temperature, when we look at a product, there is this amorphous region and a crystalline region, and this is why the material is called semi-crystalline. But how can we see this difference in practice? One very visible difference between amorphous and semi-crystalline plastics is their transparency. It is easy to believe that these little crystals block or reflect light in a way that semi-crystalline plastics are not transparent in general. There are some exceptions like PP random copolymer, which can be maybe described more like a translucent than transparent, but this is a topic for another video. However, if you're looking for kind of a crystal clear clarity and glass-like transparency, it is likely that you will find your material within the family of amorphous plastics. But then you have to keep in mind that amorphous plastics have their common weaknesses that I will present later on in this video, and you have to deal with those with your design. I will have an imaginary mold cavity here. Let's say dimensions are 100 times 100 millimeters or whatever units, and we gate it from down here, so the plastic flows more or less like this. So this is the direction of flow and this is the direction perpendicular to the flow. Amorphous plastics, they don't shrink that much in the process, only 0.5% or so. So what we end up with is approximately 99.5 times 99.5. Simple as that. Semi-crystalline plastics, they behave a bit differently. They shrink more, so in the direction of flow we get, let's say, 98.5, but in the direction perpendicular to the flow they shrink even more, and for this reason we get, let's say, 97.5. So it is understandable that due to this higher shrinkage and a bit uneven shrinkage, it is more challenging to produce totally straight and dimensionally accurate products using semi-crystalline plastics. This is very easy to see in practice. If we take polycarbonate, very typical amorphous plastic, and then POM, very typical and very crystalline, semi-crystalline plastic, and we compare their size, we can see that POM is significant, like 2 millimeters shorter or smaller than the PC sample is. I can see it like this, and if I place them on the table and try knocking the corner of polycarbonate sample and then the POM sample, I can see that and feel and hear that polycarbonate is much straighter, less warpage on that than there is on the POM sample. When it comes to surface quality, amorphous plastics tend to have this nice, shiny and dry, clean surface, as semi-crystalline plastics are easily a little bit oily. In addition to this, due to higher shrinkage, sink marks tend to be a bit more evident on the surface of a product that has been produced using semi-crystalline plastics. For these reasons and dimensional accuracy, All the housings of electrical appliances and such are typically produced using amorphous plastics. If you need to paint, glue, print or weld plastic components together, this is typically easier when you're using amorphous plastics. I have an example here. 2 samples of amorphous ABS, 2 samples of semi-crystalline polyamide 6 have both been glued together in the same way. The upper edge here. As you can see, the ABS samples stick together quite firmly. The polyamide 6 samples, well, at least what they should do is that they should come off quite easily, like this. So now you might ask that if we have these amorphous plastics that are relatively easy to process, have a nice surface finish, do not have that many sink marks, they can be painted, glued, printed or welded if needed, they can be transparent if needed. Why do we need semi-crystalline plastics in the first place? The answer is simple: machine design applications. If the function of your product requires that the plastic components move against each other, against other plastic, against wood or perhaps against metal, you need low coefficient of friction and good wear resistance. If so, you should be looking at the semi-crystalline plastics. Especially polyamide 6 and POM are known as good bearing materials. If your product is subjected to long-term static, like this for months or years, or cyclic load, then semi-crystalline plastics are much safer choice. Amorphous plastics tend to be sensitive to stress cracking and fatigue. Actually, using amorphous plastics in this type of applications is probably the most common reason for plastic products to fail. Almost every plastic product is in one way or another challenged by a strong or mild chemical attack. It might be gasoline, it might be oil, it might be sun lotion, chicken fat or some cleaning substance. Typically, semi-crystalline plastics have much better chemical resistance than amorphous plastics do. In plastic product design there is this rule of thumb that amorphous plastics are good for visually demanding components and semi-crystalline plastics are good for technically demanding components. There are some exceptions and sometimes we just have to make some sort of a compromise with the material selection and compensate that with good design. Before I end this video, I have to mention one more thing. TG, glass transition temperature. Amorphous plastics can only be used below their TG, but with semi-crystalline plastic, you have to take that into consideration. How to do that? It's a topic for another video that you can find in plasticprop.com. Thank you for watching.